Hey, welcome to my channel. My name is Danny Joseph. I'm actually going to be your host for today, and we're going to be reviewing 6 questions pulled from a Calculus 2 quiz, and we're going to see how we would go ahead and take care of each individual problem. That way, if you're ever stuck in a quiz, you know exactly what you would need to do to come out victorious on all these problems. So how about we go ahead and take a deep dive into those questions and see what we would do. So we're going to go ahead and work on this first integral that we have here for question number 1, part A. We actually have the integral of sine 7x cosine 4x dx. So right off the bat, our goal is to condense this integral down to something we can work with that's a little bit easier to manipulate. Thankfully, there's actually a formula to help us do that. So that formula, which I'll write in this blue marker here. So it's actually going to be sine A times, let me do that one more time. So it's actually going to be sine A times cosine B equals sine, actually, damn it. All right, let's try that one more time. So it's actually going to be sine A times cosine B equals 1/2 sine times A minus B plus sine A plus B. So hopefully you can see that there. So the actual formula that we'll be dealing with here is actually going to be sine A cosine B equals 1/2 times sine A minus B plus sine A plus B. That's actually going to be the formula we're going to use to help condense down the current integral that we have. So let's go ahead and plug that back to our original problem that we have, which is going to give us the following. So the integral of 1/2 times sine. Now in this case, our A and B, it's actually going to represent by the 7x and the 4x. So we're going to plug that right back into the equation that we have. So we know it's 1/2 times sine A minus B, so in this case we have 7x minus 4x plus, and then what's next in our equation there? We have sine of 7x plus 4x. And let's not forget the dx at the end, because we're still trying to find the integral in terms of x. So, with that being said, now that we have our new integral, this is where we're going to start to try to condense it down so that we can get an integral at the end that we can simply find the value of. So, now let's go ahead and look in terms of what's in the parentheses. So, we know with the parentheses here for the first sign, this is going to condense down to 3x. So we know that's going to be sine 3x plus, and this one's going to give us 11x. So we know that's going to now change that to sine 11x dx. Perfect. So we're doing well so far, and I know pure instinct you're thinking, all right, well, why don't I just do the sine 3x against the sine 11x? Slow down, because we want to make sure that we're still getting the integral of the original problem that we have. So now what you're going to want to go ahead and do is separate these integrals so we can find out what those are in terms of the value and then plug it right back in. So before we do so, let's go ahead and simplify this a little bit further to make our lives a little bit easier. So this 1/2 here is just kind of relaxing. What we're going to do, we're going to bring that out of the integral which is going to give us 1/2 integral of sine 3x plus sine 11x dx. Perfect. Now we're ready to go. So now at this point, we're going to go ahead and treat this like any other integral. We're going to make sure we keep the 1/2 out. And that's going to then provide us, we know the integral of sine is going to be a negative cosine. So what is that going to do? That's going to then create a negative cosine, but we also have the 3x. So when we include the 3x as an integral, that's going to give us then negative cosine 3x over 3 minus a cosine of 11x over 11. Now, of course, since there's no bounds, we'll put a plus c for the constant. Now, technically speaking, at this point, you can say and consider yourself done with this answer here. But if your professor requires you to condense this down a little bit further, what we can do is then go ahead and distribute the 1/2, and then see what the problem gives us at that point. So if we were to distribute the 1/2, let me go ahead and use this blue marker here. We're going to go ahead and times the denominators by 2. Since we have a 1/2 that we need to times the equation by. So what is that going to give us now? We're going to now have a negative cosine 3x over 6 minus a negative cosine, oh, I'm sorry, doing a double negative at that point. We don't want that. So then we're going to do a minus cosine 11x over 22. Let's not forget the c, and then you are all done with that integral. We are now going to go ahead and tackle question 1 part B. Question 1 part B throws a little bit different elements at us, so let's take a look at it. We have a spring has a natural length of 28 centimeters. If a 28 Newton force is required to keep it stretched to a length of 36 centimeters, how much work, which we represent by using W, is required to stretch it from 28 centimeters to 32 centimeters? All right, so we have a few things working now, and we want to kind of break this down to something that we can really digest and work through. So again, it's really important to have this prior knowledge and these formulas in your head before attacking any of these problems. So one of the formulas that we know is that W, which they represent as work, has an actual formula to it. So again, I'm going to write this on the side so we can keep note of that. So work is equal to the integral of A and B in terms of the limits and the function dx, right? But what does that really even mean? It's a little confusing because we don't have any of these variables currently. Well, we do have a couple of them. And using Hooke's law, we're going to be able to kind of decipher what elements go into this integral and then find the value after getting that. So let's kind of break down what we have so far. So it says a spring has a natural length of 28 centimeters. If a 28 Newton force is required, so we already know the amount of force, and then it's stretched to a 36 centimeter, how much work is required from 28 to 32? So with that information, let's go ahead and plug in a few variables here. So what is Hooke's law? Because you know I mentioned it earlier, but let's also write what Hooke's law is. So it says the following. F equals kx. Now, again, I'm just throwing more variables at you, and you're probably scratching your head like, what's going on? Well, let's let F represent the force. K is going to be our constant. And X is going to be the distance. Now, Danny, what does that mean? All right, well, let me break it down step by step for you. Okay, so keep in mind, we have these elements now, and it's starting to at least drive us towards what we need to solve. So we know, again, we have the force. The force is stated here, which, again, I'll highlight. The force is 28 newtons. So let's keep that in mind. And let's plug in some values. So we have 28 listed here. Now, we have K, which is the constant, but also the distance. Now, the distance is where we're going to have to get a little crafty now. We know the distance from 28 to 36 requires 28 newtons of force. So, if x equals the distance, how about we plug that in? To find the distance between 36 and 28, we'll just minus those two elements. So, what is 36 minus 28? We get 8 centimeters. But keep in mind, anybody who's taken a physics class knows that typically when we're plugging in these values into a formula, they're represented by a certain measure. So instead of centimeters, they actually use meters. But that's easy to convert. So we know it's 8 centimeters, which actually converts down to 0.08 meters. All right, so now let's go ahead and plug that back into the formula that we have so far. So we know 28 equals K times 0.08. All right, so now we're getting somewhere. We already know the force and we know the distance, but what is the constant and how will we go about finding that? Well, easy, actually. Let's go ahead and rewrite this equation so that we can find it in terms of K. Well, what we're going to go ahead and do is divide this by 0.08 on both sides. That way, the new K value that we get out of that is actually going to be K equals 350. All right. Now, of course, I did the math before this, so I already have this on the top of my head, but keep in mind now, K being the constant equals 350. Now, let's go back to our original formula. Now, since we have some of the values, we still aren't done. We still don't know A or B. And then, of course, we need to make sure that we find this in terms of X. So, now that we have some of the values here, let's keep in mind we want to find A and B. So, we know right off the bat, A is actually going to equal 0. Why? Because you're starting from a resting point and then stretching it out. But keep in mind, what is B? Well, B is going to be what the end of the question's asking us, which is we're stretching it from 28 centimeters to 32 centimeters. So we're going to find the distance between those two. And just like what we had before, we're going to go ahead and subtract the 2 and 28. So 32 minus 28, it's going to give us 4 centimeters, which is also 0.04 meters. So we know now that our B is going to be actually 0.04 meters. Perfect. So now we have that. We have what the force, what the constant is, and what the distance is. So now we're going to go ahead and plug this back to our original integral and or our formula. So how do we do so? Well, follow me down here. We're going to write the integral. Again, we're going to plug in our A, which is 0, and then we're going to plug in our B, which is 0.04. But what is our function x? Well, our function x is actually going to be the kx that we had originally, right? So we're going to go ahead and plug that in. So now that we know the value of what the now that we know the value of the k, we're going to plug that in. And again, it's going to be 350 and then x dx. Now, at this point, we have a much easier integral to work from. And we're just going to go ahead and do the simple steps that we normally would take to simplify this integral now. So the integral of 350x with the limits of 0 to 0.04. This actually now converts to 350 over 2 x squared. And then don't forget your limits, which is 0.04 and 0. Now, of course, when you plug in the 0 value, it's just going to return to you 0. But we also want to plug in our value of 0.4. So now when we go ahead and plug that in, give me one moment. I'll go ahead and find out what that is here. So what that's going to do is bring us down to 350 over 2.04 squared. All right. And then, of course, when we go ahead and calculate the value of that, that's going to give us the total of 0.28. Now, the biggest thing, again, you're not exactly done, because you want to remember as well that we're dealing with Hooke's law and we're trying to find what the work is. So work is actually measured in joules. So your final answer is actually going to be 0.28 joules. And that's also going to be, again, the work. Okay, so we have question number 2. Again, this is a 6-part series. So with question number 2, it's a little bit different. He threw us a little bit of a curveball. What we have is compute the volume of the solid formed by revolving the region bounded by the graph y equals x squared plus 1, y equaling 0, and x equaling 1 about the y-axis. So we have a few things that we've been thrown here, and I kind of already set up the the little sheet, the board that we're working on to kind of save us a little bit of time. So you notice I did a really poor rendition of what the function is, which is x squared plus 1, and what that will graphically come out to be. So this line here actually represents the function x squared plus 1, just to keep in mind so we know exactly where we're at. But we're going to be using the cylindrical method. So I already went ahead and wrote the formula for the cylindrical method, which is going to be assisting us with finding the volume. And that's going to be volume equals 2 pi, the integral with the limits of a and b, rx times hx dx. Now, if you are unfamiliar with the formula, we have Rx representing the radius and Hx representing the height. And of course, with the respects of x, which is why we have the dx there. So there's going to be a few things we're going to want to tackle here. We're going to need to find our, of course, we're going to have to find our variables so that we can plug it back into the integral so we can find our final value, so we can find out what the volume is for this. Now, you'll notice if you just plug in the x squared plus 1 function to find out how that looks on a graph, you're actually just going to have this right-hand part of it. The reason why we have it looking more like a U shape is just like what they stated here. You're going to be revolving this about the x-axis. So unfortunately, again, hopefully you guys can see that. That's a really poor drawing, but essentially just imagine rotating this function across that y-axis, which will give you somewhat of that U shape. Once you have that U shape, you're going to want to kind of make your own rendition of a cylinder, and then that's essentially what we're going to be finding the volume of. So now that we kind of broke down what we have on the board itself, let's go ahead and go about solving this. So we have a few variables on here that we don't know the value of. So we're going to start with finding the values of those. So we already know right off the bat that R is actually going to represent X. All right, knowing the formula that we are already dealing with, we know that R equals X at that point. Now, what about the H value? Well, the H value is actually going to then represent the function that we have. Because if you notice, when we're going about that function here, it kind of wraps over that cylinder that we create, giving us the height that we're looking for. So we're going to go ahead and assign the value of H to the function x squared plus 1. All right, so we're cooking with oil. We're getting somewhere with this. So now at this point, what we're going to want to go ahead and do is plug this back into the formula. Now I know you're thinking, what about A and B? Well, we already actually have A and B, surprisingly enough, because again, if you notice, the limits, the 0 to 1 is where that function starts. We're going to use those as our A and B. And again, what you'll notice, from the y-axis, that 0 to 1 is where the original function starts from. So we're going to keep that in mind, even though we're rotating it about the y-axis, that the original bounds is from 0 to 1. All right, so now let's go ahead and plug back in those values that we have. So we have the volume equaling 2 pi integral. We know A is going to be 0, since that's where we're starting from, and B is going to be 1. And then we have our R, which is x, times the height, which the height will be x squared plus 1 dx. Now, let's go ahead and condense this down a little bit further. So, again, we'll have 2 pi 1, 0. Now, what can we do? Well, we can disperse the x across the problem here. That way it gives us our new integral. So that's going to be x to the third plus x. Because we know x times 1 is just x. And then, of course, our dx. Now, we're doing pretty good. The integral isn't looking too crazy, and we can definitely work with x cubed plus x dx. Now, again, we're going to go ahead and find the integral of that. So we have 2 pi outside, and we know we're going to have to times that by... Now, again, if you're not familiar, what you'll go ahead and do is you'll do the exponent 3 plus 1, and then divide it by the exponent value plus 1. So what is that going to do? That's going to give you x to the fourth over 4 plus x to the second over 2. Then let's remember our bounds, which is 1 and 0. And then from there, again, we're cooking with oil. We're getting through this problem, and it's seeming a lot more feasible in terms of finding the value. Now let's go ahead and continue to simplify this problem. So we have 2 pi. Now, thankfully, we know anything including 0 is just going to zero itself out. So let's just primarily focus on the 1. So we'll replace the x value with the 1 to the fourth over 4 plus 1 to the second over 2. Perfect. So now we know anything 1 to the whatever power is going to equal 1. So we basically know that 1 over 4 plus 1 over 2 is what we're going to end up with. Well, how do we condense that down? Well, I'll go ahead and draw an arrow so it just kind of shows what we're doing here. We know that we're going to have to find the common denominator for us to go ahead and add that together. So again, we have 1 over 4, but what's the common denominator? Well, it would be 4. So we would need to times both ends by 2. So what is that going to give us? Plus 2 over 4. And then altogether, that's going to give you a value of 3 over 4. But we're not done. We want to plug that back in because we have that still in terms where we want to multiply that by 2 pi. So now, again, if we bring that back over, we have 2 pi times 3 over 4. Well, what is that going to bring us to? Well, we know that if we times 2 pi across the board here, you're going to just want to focus like this was 2 pi over 1. So you know the 2 pi is going to be multiplied by the 3, and we're still going to keep the denominator of 4. So that's going to give you 6 pi over 4. And again, we're not done yet because we know that they actually can be canceled out to reflect 3 pi over 2. And that will be your final answer there. We're on question 3. And question 3, I'll tell you, man, it's a doozy. So I want you to strap in. We got a lot of things we got to tackle, but there's some things I want to go ahead and break down with you, just so you have a better understanding of what we're doing in the problem itself. So let's keep a couple things in mind, right? So right now, question 3, right off the bat, it says compute the volume of the solid formed by the region bounded by the graphs y equals sine x, y equals cosine x, from 0 being less than or equal to x, and then pi over 4 being greater than or equal to x. So keep in mind while it's being rotated about the y equaling minus 2. So I know that's a mouthful. It was a mouthful for me. Let me just break it down a little bit, because I'll tell you, when I was doing the quiz, I was freaking out. All right, what is this mathemagics that he's throwing at us, right? So first and foremost, you want to break it down part by part. We know, one, we're computing the volume. So we know that we're going to want to use a formula that's related to computing the volume. But we don't know right off the bat. I know we have this here. Let's disregard that for a moment. First and foremost, you want to make sure you're graphing the problem properly. So again, it is finding the volume between these two graphs. So let's graph those first. Let's see what they look like. So I already presented that here, just so you guys can get a little bit of a representation. I hope you guys can understand what we have here. So we have our first line representing the function of cosine x, which is y equals cosine x. And you're going to notice it kind of loops around, because that function, that's just how it represents itself on a graph. But we also have sine x, and that kind of does the opposite. So you have this like interweaving that they have going on in the graph. So of course, we're particularly focused on this region in particular, and you're probably wondering why. Why that region in particular? Well, you want to remember that they want us to compute it based off the bounds of 0 and pi over 4. So, ironically enough, this section here represents pi over 4. Right? Okay, so that's fair enough. So if we already know that the regions are 0 and pi over 4, well, let's take some more things into account. Well, it's saying that it's being rotated, but it's not just by the y-axis or the x-axis. It's actually from minus 2. So that's a little bit different from rotating against the x and the y-axis. So x minus 2, you're going to want to think, y minus 2, you're going to want to think it's between this whole little region that I'm kind of marking up in blue. That's going to affect how we go about this problem in a little bit. So keep that little section in mind based off how much distance we have from our original functions. Now, typically, if we're finding the volume, we have several methods on how we can do things. I know on the last problem, we talked about using the cylindrical method, but I'm going to use a method that I'm greatly familiar with and that I actually prefer over most methods, and that's the washer method. So if you notice here, I actually drew a little bit of a rendition of a washer as best as I could to kind of give you a representation of what we're dealing with. So let's look at the formula. So the formula says to find the volume, it would be pi in the integration of the bounds of a and b with the capital R representing one of the radius to squared, of course, and then minus the other radius, which is represented by a lowercase r squared dx. So we're looking in terms of x, all right? Now, keep in mind, let's go back to this washer that we have here. The reason why there's a capital and a lowercase r is because we're representing both radiuses, but the smaller of the radius and the larger of the radius. Now, keep in mind here, when we're talking about a smaller amount of the radius, when you're rotating this against the -2 here, you can then somewhat draw a washer in between those two functions. Now, when you draw that washer, there's going to be a smaller circle and then a bigger circle. That smaller circle is actually represented by the small r. The larger circle is actually represented by the big R. So we know there's going to be two different types of radiuses, or radii, I guess you can call it. So you can go ahead and look at it as such. So we know the larger of the radii is going to be the cosine. Okay, so the cosine will be here, cosine x, and the smaller would be the sine x. And if you don't believe me, of course, draw your own graph and then rotate it about that -2, and you'll actually see that since the cosine is out, that's why it's the larger of the two, and since the sine is actually the inner function, that's why it's the inner of the two radii. So now as we go to actually find the bounds, we already know that a is going to equal 0 and b will equal pi over 4. Beautiful. Less thinking, I'm all for it. That's what I'm talking about. But when we're looking at the radiuses, or the radii like we were mentioning, we want to keep some things into account. Notice how I went ahead and highlighted that region, that -2 region earlier. That's affecting how we go about this problem, because now we have to take into account the larger amount of a radius that we would have because it's been extended that much. So when we're looking at the capital R function here, we're going to look at cosine x, but we're going to actually add the additional portion to that region, which is 2 in this case. Even though it's a -2, it's still a positive value that we're adding to it. So now this is actually going to change into 2 cosine x. So of course we would do the same for the smaller r here, which will be 2 plus sine x. Perfect. So now that we actually got that out of the way and we have our a and b, we can start plugging these values into our volume formula. So let's go ahead and do so. So again, we have v equals pi, which doesn't change. And as we integrate it, we're going to say a equals 0 and b equals pi over 4. So now we're going to look back to our capital R, which we know now is going to be 2 plus cosine x squared minus 2 plus sine x. And let's not forget the square and our dx, which tells us it's in respects of x. Now, this is a lot to kind of throw at a person. So I promise we're going to condense it down so you can work with it a little bit easier. So first thing we're going to do is we're going to look at these two and factor them out so we know exactly what we're dealing with. So I'm going to go ahead and write that here. But again, we're dealing with a limited space size, so bear with me for a moment. So we're going to use this little corner space to kind of factor everything out. So we know if we have 2 plus cosine x squared, we're going to be basically factoring these two here to get the full value of what we're dealing with in terms of the integral. So let's bring this down. We'll bring this down here so we have a little bit more space to write. Actually, we might need a little bit more space here. So we have the volume now, and I'll draw a little line separating that. So we have the volume pi integral 0 and pi over 4. And then now we're actually going to have, if we do the factoring, it's going to be 4 plus 4 cosine x plus cosine squared x. Then we're going to do the same to the other side. So minus, remember we have the minus, and it's going to look almost identical. So we're going to have 4 plus 4 sine x plus sine squared x. And then again, dx. We can't forget that dx now. So now you're probably looking at me like, Danny, that looks a lot more than what we had previously. And I understand that, but it's for a purpose. Now let's go ahead and break some things down. Now, if you notice, we have some like terms. So right off the bat, what I'll go ahead and do and represent that here, the 4s are going to cancel those stuffs out because we have a positive 4 and technically we have a negative 4. So we're going to go ahead and cancel the 4s out. So there we go. We're already simplifying this as best as we can. But we're going to go ahead and rewrite that so we know exactly what we're dealing with. I know it's a lot of rewriting. I know what you're saying. You're like, I don't want to write all this out. I get it. I understand. But again, what we're now going to have is 4 cosine x plus cosine squared x. Again, where I left off is we went ahead and canceled out the 4's. So now we're going to go ahead and rewrite the equation as such. We have volume equaling pi, an integral from the bounds of 0, pi over 4. And then we have 4 cosine x plus cosine squared x minus 4 sine x plus sine squared x dx. We know right off the bat these two terms, which actually I will use the blue marker here. Cosine squared x minus sine squared x is the same as actually just saying cosine 2x. So we can actually rewrite this even further to the following and simplify it. So now we have 4 cosine x minus 4 sine x. And then again, it would be actually a positive cosine squared, or I'm sorry, cosine 2x. So what that's going to look like now, it's going to be cosine 2x. And then again, dx. This is actually a formula that we find out in previous classes here. So we can apply that to this aspect. So now that we know that this is the condensed version of the original integral that we have, now we can start going ahead and finding the integrals of these separate, the 4 cosine x, the minus 4 sine x, and the plus cosine 2x. Now, keep in mind, you got to be very careful when you go to find the integral of these things because it's very easy to make a mistake. So I'll go ahead and kind of break that down at this point. Let me go ahead and make sure I have some board space. This is where we left off. For cosine x minus 4 sine x plus cosine 2x dx. All right, so that's where we just left off. So again, now we're going to go ahead and find the integral of these things. So now that we're finding the integral, I'll go ahead and bring it right over here. The volume equals pi times, so we're going to look at the integral of 4 cosine x. So for cosine x, we know the integral of cosine x is actually sine x, exactly. So we're going to plug that in for sine x. Then we're going to look at this one. So what is the integral of minus 4 sine x? Well, we know the integral of minus sine x is actually a positive cosine x. All right. And then we have our final integral of cosine 2x. Now, the thing to be wary about that you have to keep in mind is we had the 4's previously in front of the cosine x and the minus sine x. So when we go to integrate them, since they were constants, they stayed with the actual integrals themselves. But now that we have cosine 2x, it changes how we go about things. Now, we know the integral of cosine is sine. But because we have the 2x, it's actually going to then become sine 2x over 2. Why? Because normally it would be 1 half sine 2x, but it's the same as saying sine 2x over 2. All right, so now that we have that, we keep in mind our bounds and or limits, some say. So we have the pi over 4 and the 0. So we want to go ahead and plug that back in to our original problem here, which probably based off the space I'll probably put down below it. So we're going to go ahead and do that. It's going to be pi times 4 sine, and that's going to be pi over 4 plus 4 cosine pi over 4 plus sine 2 pi over 4 over 2. And then that's going to be minus, so we'll just kind of keep that in mind, minus, now we'll be plugging in the 0 value. So 4 sine 0, and I'll put parentheses now so I don't forget, 4 cosine 0 plus sine 2 0 over 2 and the ending bracket there. So now that we know what those bounds are and we've computed it, let's condense it down a little bit further. So what I'll go ahead and do is try to rewrite this here at the top. So after integrating it, we're going to find out that those simplify now to pi times 4 square root of 2 over 2, or root 2 over 2, plus 4 root 2 over 2 as well, plus 1/2. Okay, that takes care of the first one. And then the other one, it's a lot simpler because we're actually dealing with zeros. Surprisingly enough, this actually just becomes 4. Okay, and of course we're going to go ahead and put brackets over that. So that's actually what it condenses down to, and then we're going to go ahead and simplify it even further so we can make this a lot easier to deal with. So one thing that you'll notice to make this even simpler is that we have 1/2 and minus 4. So we can just simply solve this right out the gate, which is going to give us -3.5. That's going to give us pi times 4 root 2 over 2 plus 4 root 2 over 2 minus 3/2. Now when we go ahead and distribute our pi and we condense down what's in the center of this function here, we're going to go ahead and get the following, which is 4 root 2 plus, sorry, forgot we had actually a negative there, -7/2 and then of course as we go to times everything by pi, we're going to then get 4 pi root 2 minus 7 pi over 2 as our final answer. So we're on question number 4 now. So man, we're more than halfway through this quiz. We're looking good, but now we got thrown something a little bit different. So we have question 4 saying solve the integral of sine square root x dx. So there's going to be a little bit of difference in how we go about actually finding out the answer to something like this. So we're going to go ahead and think about the ways that we can solve an integral like this. One way that comes to mind, and the way that I'm going to be using for this particular method, is going to be the substitution method, the U substitution specifically. So we have our integral here, and we're going to think about what in this integral is very complex that we can't just solve outright. Right now, what jumps at me is actually going to be this square root of x. So I want to do something to that square root of x to make this a lot easier to deal with. So what I'm going to go ahead and do is right over here what we intend on using for substituting. So we already discussed it. That root of x seems like something we would want to kind of substitute out. That way we don't have to deal with it immediately. We can kind of work this integral in an easier way and then come back to it later. So what I'm going to go ahead and do, and the reason it's called u substitution, I'm going to go ahead and use a variable u. Now technically this is kind of like a placeholder. So you can use t, w, v, whatever you would like to use. Just know it's just going to go ahead and replace the value that you have currently in the integral. So I have u, and we're going to go ahead and have u equal the root of x. But keep in mind, we need to find du, which is a derivative of that. So we know that if u is equal to root x, then du has to equal 1 over 2 x to the negative 1/2. And let's not forget dx, because it's in respects of x. But that's still kind of ugly. I kind of still want to condense that down, because we could actually condense it down a little bit further, because we know that x to the negative 1/2 is the same as saying root x. So why not just replace it with another u? So let's go ahead and do that. So we know that du, in fact, actually equals 1 over 2, and then we're going to say root u. How about that? Oh, I'm sorry. Complicated our variables there. So we're actually going to say du is equal to 1 over 2 root x, because that's what the variable's in terms of at the moment. And of course, let's not forget the dx. But what if we just have dx? How can we find the value of what just dx represents? Well, simple. How about we go ahead and multiply the 2 root over x onto the other side to get rid of that. That way, then in terms of that, we'll have 2 root x du equals dx. That way, we know what dx represents, and we know what, if we need it, du represents. But we've went ahead and substituted out the more complex part, and we have some values we can go ahead and plug back in. So now as we look back into our original integral, we're going to have the integral of sine, and then we're going to go ahead and plug in u. Now, of course, we have to look at this integral in respects of u now. So we have to use, instead of dx, we have to use du. And now we know what dx, the value of dx is. It's actually 2 root of x du. So now we're going to go ahead and substitute that back in. So we're going to have 2, and then the root of x is actually u, so we can say 2u and du. So if you follow what I did there, again, we had the 2 root x, we multiplied that over here, but we know that root of x is substituted by u. So we can then assume that the 2 root of x now changes over to 2u, and of course du stays the same. So now our new integral reads sine u 2u du. So of course, now that we have that there, we're going to go ahead and we haven't really solved much of anything. We still want to go ahead and condense this a little bit further so we have something more to work with. So how about, I know it's kind of wild, but how about we do another substitution? So we're looking at a substitution within a substitution. So with that, I know we have this here. I'm going to go ahead and use black again. And we're going to go ahead, just like how we did for u, we're going to say, let's just say w, right? So we're going to say w, and we're going to look in terms of replacing the 2u. But keep in mind, when we're doing something like this, where we're doing a substitution within a substitution, we have to keep in mind, we want to substitute something that will break down eventually, hopefully, to 0. Now, keep in mind, if we were to do something like that, we have to do another variable here. So we'll say this will be 2u, which will give us a dw of 2 du, and then we'll look in terms of dv and v. Now, dv we'll use for the other end, which we have is sine. So we'll do dv equals sine u du. Okay? And then at that point, we know that the antiderivative of sine is negative cosine u. Okay? So, hey, like I said, we're cooking with oil at this moment, so we're getting somewhere, but what's really going on? Because we have a substitution and then another substitution. Well, we know now, since we've done that, there's a new formula that we have to plug in. So now we can go ahead and say, because that formula is going to be the uv minus the integral of v du. All right, so keep that in mind. So we're going to go ahead and plug in our values here. Now, in this case, instead of u, we're going to be saying it's going to be w, since we already had the u value. So what I'll go ahead and say, it's going to be w v minus the integral of v dw. And we have that there. So we're going to go ahead and plug those values in. So the u, or the w in this case, is going to be 2u times v, which is negative cosine u, minus the integral of v du. So v being negative cosine u, and then du, or dw, which is 2 du. Perfect. So again, I'll go ahead and block this off just so you know we're using that more as our table and our values. So how do we go from this to there? Again, we plugged in those values knowing that this in particular was our formula that we're using. So now, since we have that and we're going to plug that over, keep in mind we want to make sure we condense this down. We're not done here at this point. So what we can do, we can bring, and I'll use the blue marker, we can actually bring this constant value of 2 out of the integral, and we can also then distribute what we have within these parentheses. So what is that going to leave us with? Well, let's look at it now. And keep in mind, actually, now that we're looking at it, we can also bring out the negative. So we're going to be bringing out two things, the negative and the 2 out in front. So what is that going to do now for us? That's going to make it now 2u, oh, actually there's a negative in front of there. So that's going to make it negative 2u cosine u. And then since we're bringing out a negative to another negative, that's going to make it a positive. So we're going to have positive 2, then the integral of cosine u du. Right. So now you can kind of see why we were doing the things we were doing, is to condense it down so we can work with things that we're normally more familiar with working with. So now we know what the integral of cosine u is in respects of u. That's actually going to give us sine u. So we'll go ahead and plug that back in, and since there's no bounds, it's going to be a plus c. So let's plug that back in so we can see what we have. So we have negative 2u cosine u plus, and again it's going to be 2 times sine u. And then we can't forget our constant, which is at the end. But again, we're not done, because we started out with x, and we have to still solve this problem in respects of x. So why don't we plug back in the values that we had originally for that? So we have u, so we'll just go ahead and plug back in what we had in terms of u. So we had a root x. So now you actually have 2 root x cosine, and then within there we have root x plus 2 sine root x plus c, and that's going to give us our final answer. So I'm actually going to go ahead and clear some space so you can kind of see what that final answer is actually going to tally up to be. Again, we have -2 root x cosine root x plus, and then I'll just multiply that out. So we're actually going to have 2 sine root x plus c. All right, guys. Now we're on question number 5. And guess what? With question number 5, you know what that means? We're almost at the end. We can see the light at the end of the tunnel. But let's get down to solving the integral of cosine x, cosine to the 5th power sine x dx. So again, it's with the respects to the x, and when we're going to go ahead and solve this integral. Now, there's a few things we want to keep in mind because there's a lot going on. We're probably going to end up, as we start to evaluate this integral, using this u substitution like we did on the previous problem, but we're going to get a little bit more creative with this, okay? Because it's not just the substitution we'll be using, but you'll see a little bit further down the road what the u substitution allows us to do. So straight off the bat, we have a lot of cosines going on, and we have this random sine x. This random sine x is, I don't know, it's giving me a little bit more of an issue. So I figure, why not we just u substitute the sine x, since it's the one that's kind of making things a little bit uglier. So let's just say we have u equal to sine x. Well, again, if we get the u, we know we have to get the du. So what does the du represent? Well, the du represents cosine x dx. Well, what does that mean? Well, guess what? We have u equaling sine x and cosine x dx equaling du. Well, we already know, thankfully, we have that. So we already have a cosine x and a dx. So technically, we already have du. And then we have u. So if you can't really see what I'm mentioning now, let me go ahead and rewrite that so it makes a little bit more sense. So now, again, we still have the integral, but now we have cosine x dx, which is going to be du, so we'll save that towards the end. But we have cosine to the 5th power, right? And instead of sine x, we have u now. So we have u, and then again, we have a du because of cosine x and dx. So wow, that automatically is already looking a lot better. But that cosine to the 5th, it's still a little ugly, and there's more we can do with that. So would you argue that cosine to the 5th is the same as saying, let's just say, cosine to the 4th u times cosine u du? Wouldn't that technically just be the same thing that we're rewriting? But you're probably wondering, why would we want to rewrite it like that? Well, the reason is we can actually derive a trig identity that we know from prior into this integral now with what we have set up. What trig identity that is, let me go ahead and show you. So we'll go ahead and move over to here, and we'll go ahead and rewrite that now to show that cosine u, and then cosine to the 4th power u is the same again as saying cosine to the 2nd u to the 2nd power. Because we know if we're squaring that, we're going to add those exponents. And then again, we still have du. So perfect. So why did I go ahead and focus on this here? Well, if anybody with an eagle eye will see that that is actually a trig identity that we know. So what is that trig identity? Well, that actually is going to convert this integral even further to cosine u. And then now what we have in that parentheses, it's going to be a 1 minus what? Sine square u. But remember, it was squared, so we have to bring that over. And then again, it's still in terms of u. So that's the reason why we were kind of going about it that way. But why would I trade up our original integral for something like this? Well, again, integrals they're tricky. You want to continue to work at it. So we're going to go ahead and replace this with another substitution. But we can't do a u substitution because we're already using u. So I'm going to go ahead and use something like w. So we'll do w. So what do we want to substitute, though? Well, I still like that cosine u because it's simple. But that sine square u, that's a little bit more ugly. So I'm going to go ahead and separate that and maybe just do sine u. So let's do sine u. And then we're going to go ahead and find dw. And we know that the derivative of sine u is going to be cosine u du. Now you see our train of thought and why we would do something like that? Because again, we have cosine u du. Don't we already have the cosine u du here? So really, we already have dw. And then again, we can go ahead and substitute the sine u as a w. So let me go ahead and rewrite that there. I know, integrals are crazy. It's like math within math. It's like kind of like math magics, you know? Kind of like what I mentioned before, but we're going somewhere, I promise you. So again, now we're actually going to have 1 minus the w squared, because again, it's sine squared u, not sine u. So it's going to be w squared. And then again, we had another square out. And then since we had cosine u and du, we know that equals dw. And that's going to be our new integral. And that's a lot easier to deal with in terms of finding an integral for that. So how about before we go to jump into this integral, because we need to simplify this a little bit more, we go ahead and we're going to distribute the square. So we know that if we're going to square it, we're going to square that. So that's still going to be 1. So I'll do the integral. So we're still going to have 1. Then we're going to have a minus 2w squared. Then on there, we're going to also have a plus w to the 4th. Okay, and then again, in respects of w. So that's what you're going to have after you square everything. So at that point, what would you want to do now to get this figured out? Well, we're going to find the we're going to integrate this, and this is a lot easier to integrate because we know with 1, we're going to go ahead and consider that a constant, and then the 2w, and we're already familiar how we're going to go ahead and do so because all we're going to go ahead and do is add 1 to the exponent and then put it over the exponent plus the 1. What does that mean? How does that look? Let's go ahead and break that down a little bit further. So what that's going to go ahead and simplify to, I'm just going to use this down here, is we know this is going to conform to w because it's 1. We're going to do minus, there we go, it's going to be 2w to the 3rd over 3 plus w to the 5th over 5 plus a constant. We can't forget the constant. Now, again, we started the integral with x's, and now we're in w's. We've gone through u's, w's. What's going on here? Where are we getting at? Okay, well, bear with me. Since we've worked to this portion here, I'm going to free up some more space. Honestly, at this point, I'm thinking I should have just got a bigger whiteboard because Calculus 2, man, I'm telling you, it's a lot of work into one problem. If you mess up in one area, well, you better just count yourself out at that point. So we're going to rewrite this here just so we know what we're dealing with. We got w minus 2w to the 3rd over 3 plus w to the 5th over 5. Oh, and plus c. Look at me. All right. So now what we're going to go ahead and do, because we want to go back to in terms of x, we're going to plug back in those values that we had previously. So we know now that if we have a w, that just represents u, the sine u. So realistically, we're going to go ahead and look at it more like we have w, which is sine u. We'll go ahead and do equals w equals sine u minus, we have a 2w, so that's going to be 2 sine u to the third power over 3 plus, you guessed it, sine u to the fifth over 5 plus a constant. Are we done though? Because I thought we started with x and we still have u's. Well, let's look at the values of u's. We know that u represents sine x. So we need to plug back in the value of u. So now what we're going to be left with is sine, and we know the u value is sine x minus 2 sine u, so that's going to be actually sine x to the third power over 3 plus sine, again we're replacing that u, sine x to the fifth power over 5, and then again that constant. Now we have everything in terms of x, just like how we started the integral. We have our constant, and we can no longer simplify these values. So that, in terms, is our answer. All right, ladies and gentlemen, we are on the last problem. I am super excited because you know what this means. If you're on the last problem, that means you are almost done with this quiz. Okay, so we have one more question to solve. It's question number 6, and it is the integral of x cubed times the root of 1 minus x squared dx. So there's a few things we're going to do. I know we're already familiar with the substitution method, and we're going to be doing something similar, but we're also going to be doing a trig substitution, and this is a little bit different. So I actually already looked up the formula for you, so it's a lot easier, and we're going to save a little bit more time. But in that trig substitution, it says that the root of a squared minus x squared is equal to a sine theta, which is equal to x. Okay. Now, what does that mean specifically? Okay, let's look at it here. If we look at the root of a squared minus x squared, well, we technically already have that if you think about it. Let's take a look over at the 1 here. Well, think about it. Well, what's the square root of 1? 1, right? So really, we do have that a squared, and we already have that x squared. So we can use this formula to make sense of everything. So with that being said, if we know that now a must equal 1 because we know the root of it is within this formula, then we can say that a now equals 1. But it also says that 1 sine theta is equal to x. So how about we plug in the value of x into our original integral? And of course we have dx, because then when we start plugging in values, we can also plug in the value of dx, since we won't be dealing with it in terms of x, we'll be dealing in terms of theta. So let's go ahead and switch some things around. Now, bear with me, because I know this looks like mathematics, but hold tight here. So we got the integral of x cubed, which we know our x is 1 sine theta, or we can just now say sine theta. So I'm going to say sine theta, and we know it's cubed. So sine theta cubed, and then we know it's times this here, which we have 1 minus x squared, right? So we're going to say 1 minus sine theta squared, right? And then we have a dx. What was dx? Cosine theta d theta. So it's going to be cosine theta d theta. So now we're looking in terms of theta, and we have everything converted in terms of theta. So that was the first step. So what do we do from there to make things a little bit easier for ourselves? Well, I don't know if you've noticed this from a previous problem, but we have another trig identity. From the previous problem, we know that 1 minus sine square theta is actually, and I'll rewrite this, sine theta, and I actually put that in front so we don't confuse ourselves. It's actually going to be cosine squared theta. And then, of course, we still have the cosine theta d theta outside. So you can see how we're already condensing things down. But what happens when you have a square root, or I'm sorry, a squared variable in a square root? We get rid of it, right? Well, before we get to that part, let's go ahead and condense down a little bit further so we know what we're walking into. Well, with that being said, we're going to have sine sine cubed theta, and then we're going to have times just a cosine theta times another cosine theta d theta. So I know you already see something simple that we can go ahead and condense down to, which is these two here. And that's going to give us, ironically, another cosine squared theta. Times cosine squared theta d theta. Okay. So now you're probably looking at this like, okay, well, that was some trickery form of mathematics, but what else can you do now at this point? Well, I want to condense some things down, and that sine cubed theta looks real ugly. But what can I do to do that? Well, I know that we can maybe make a trig identity out of sine squared theta, but we don't have sine squared theta. Or do we? We actually do. Because this sine cubed theta could be condensed or rewritten as sine squared theta times sine theta times cosine squared theta d theta. So now if you see here, we have sine squared theta, which we can then convert into one of the trig identities that we remember. So instead of having the 1 minus sine squared theta, well, we have sine squared theta here, which that converts over to, you guessed it, 1 minus cosine squared theta. So I'll go ahead and rewrite that here. It's perfect. So what we're going to go ahead and do now, since we have that, now we can consider some different methods of how we're going to go ahead and simplify this even further. Well, again, if I were to want to condense this down, I'm seeing a lot of cosine thetas. So why not substitute that? That way we can make this a little bit prettier. And we can use a u substitution to do that. So I'm thinking, how about, and I'll put this in blue so we know what we're dealing with, u equals cosine theta. So that'll make du equal a, you know what, I'm going to make it equal a negative du equals a sine theta d theta. And you'll see why I did that in a moment. So now, when we look at that, we're going to plug that back into our original integral. So now, or with our original integral before the u substitution, I should say. So now we have this, and we're going to go ahead and convert that. So it's going to be a negative 1 minus, now we know that u equals cosine theta, and we have cosine squared theta, so we're going to say 1 minus u squared, and go ahead and consider that we have another cosine theta out there, which is squared, so we'll say u squared. And then think about what we had before. So we also had a sine theta d theta equals negative du. So technically, we would be bringing out another negative into this problem, if I'm correct of thinking that, right? So let me go ahead and I'll put a negative du. And that's going to solve our issue with the sign that we had out there. So now we're condensing this down a lot better, but again, we still have some elements we want to deal with. So how about we go ahead and simplify this a little bit further. So what I'm going to go ahead and do is look at it like this. I'm going to bring out, and just so you know where I'm at this point, I'm going to, I don't like that negative du, so I'm going to bring that in front of our integral here. So just like before, we have like a -1, we're bringing that -1, quote unquote. So now we have a negative, and then here, again, we have negative, we'll say, we'll kind of times this by itself. So we'll say negative u squared plus a positive u to the 4th du. How's that? So now as we look at that, we are proposed a few ways in how we can look at this problem. I'm still thinking we can simplify this a little bit further. As we look at this problem here, I think that we can go ahead and do the integral of this. So I'm going to go ahead and do the negative of u to the 3rd over 3 plus u to the 5th over 5. And then, of course, we have a constant, which is c. All right, and then, of course, we definitely don't want to forget the negative here. All right, so now that we have that there, I can get rid of this integral since we've simplified that a little bit further. But the problem is, just like with other problems that we've had before, is we have this in terms of u. We need to get back to x. And how can we do so? Well, we have to plug in the value of what we had for u in for the problem that we have currently. So once we do that, we know that we're going to have a cosine theta. So we have cosine theta to the cubed over 3, and then we're going to have minus cosine theta to the 5th over 5 plus c. But Danny, I know what you're saying, but Danny, you have these things in terms of theta, not in terms of x. So what's going on here? We have to change this up a little bit. Again, when we're doing substitutions within a substitution, we have to remember the values that we have. But we use a trig substitution. So how we go about finding that, it's going to be a little bit different. So bear with me now. If we're going to find that, we know that sine theta equals x. Or, I'm sorry, a sine theta equals x, which is 1 sine theta equaling x. Well, couldn't we also say that sine theta, if we divide sine theta 1 across on each side, we can also say that sine theta is x over 1. Would I be correct with that assumption? I would think so, right? Well, if sine theta equals x over 1, then we know that sine theta, or sine, represents opposite over hypotenuse. Well, why does that matter? Well, let's create a triangle. And when we think of the triangle, we're going to think of the angle in theta. And we know we have the adjacent, we have the opposite, and we have the hypotenuse. Well, we just said the opposite and the hypotenuse is x over 1. So the hypotenuse would be 1, and the opposite side would be x. Okay, so now that we know that the opposite side is x, and we know that the hypotenuse is 1, what is the adjacent side? Well, to find that, we know the Pythagorean theorem says a squared plus b squared equals c squared. Well, technically we already have c squared, and we already have, let's just say, a squared. So we have to do c squared minus a squared equals b squared. So with that being said, if we're looking in terms of what this value is, so let's say b squared equals c squared minus a squared, we plug in that value, it's going to be, we know that c squared would technically be 1, and then a squared would be x squared. And then, of course, in terms of b squared, which b is just a placeholder value, and then for b, since we're looking in terms of b, that's going to be the square root of 1 minus x squared. So that's what we plug in for the adjacent side, which is 1 minus x squared. Now, again, you're probably wondering, why are we even doing all this? Well, I'll tell you, there's a purpose, there's a method to the madness, right? So now that we know these values, how can we determine then what cosine means? Well, we know cosine means that is also equal to adjacent over hypotenuse. So in a way, we just found out what the cosine value is, because we know now that if that is the adjacent over the hypotenuse, we know the adjacent side is 1 minus x squared and the root of that over what we already determined the hypotenuse being 1 equaling cosine. So now that we have that, we can plug that back into our original problem. So now we can now say that cosine cubed theta is going to be, and this is where it's dangerous how you write it, but it's going to now be the square root of 1 minus x squared. And we know since it's over 1, we can just consider that as is. Cubed over 3 minus the same thing. So we're going to have 1 minus x squared to the 5th power now over 5 plus c as a constant. And that will return us back over to things in terms of x. And we have our constant giving us the final value of the integral. So we got the 6 questions done and over with. We're done with the quiz, and hopefully this was helpful. If it was, don't forget to smash the like button, like, comment, and subscribe, and let me know what I can do in the future to maybe do this a little bit better. Hopefully my professor out there is proud of the video that was created, and hopefully I provided you some correct answers. If anything, stay tuned, subscribe to the channel for more videos like this. Have a great day.